In the third block of this multivariable calculus series, we're going to talk about integrals. This first video will focus on the one-dimensional integral, and we'll talk about what the integral is and the derivation for the formula for calculating it, as well as some important techniques for calculating integrals, such as integration by parts and substitutions. We will also mention the partial derivative and the gradient at the end. Let us start from the beginning. A classical formula from physics is that the distance traveled is the speed multiplied with the time. We can write the time as the difference between the end time and the start time. Now assume that we create a graph with the velocity on the y-axis and time on the x-axis. Let the green line represent the speed and mark the start time and end time. We know that the area of the rectangle is the height times the base. Hence, we can write the area of the green rectangle as v times t end minus t start. This means that the distance traveled can be represented by the area of this rectangle. Here we are visualizing the distance as the area under the graph, as they are calculated with the same equation. We are not actually claiming that the distance is the area, because that would be problematic as they have different units. The rectangle representation works if you have constant speed, but what if the speed varies with time? The key aspect of this visualization is that the representation of S as the area under the graph still works. The only question is how to calculate it, as the rectangle formula clearly does not work anymore. Let us leave the distance traveled example for a bit and simply have x on the x-axis and f of x on the y-axis. Call a start point xs and end point xe, and assume that we want to calculate the green area A. One way to approximate the area is to divide the x-axis into smaller segments. Define the sequence x0 to x10 along the x-axis, where xs is x0 and xe is x10. The sequence should be strictly increasing. Here I have called the finite element xn. Now, we can create rectangles between the points in the sequence, and claim that the area can be approximated by the sum of these rectangles. We know that the area of one rectangle is the height f of x times the base delta x, where delta x is the difference between 2 points. Note that the number of rectangles always is 1 less than the number of points, hence the sum ends at 9. Let us rewrite the sum though to include an arbitrary number of points n, hence the sum ends at n minus 1. Let us also remember the derivative, which is the slope of the curve delta f over delta x, or the limit of f xi plus 1 minus f of xi over delta x when delta x goes to 0. Note that xi plus 1 is xi plus delta x. Now we're going to introduce the primitive function capital F, such as f is the derivative of this function. Let's insert the primitive function in the definition of the derivative. We can write the derivative as f of xi according to the definition of the primitive function. Let us drop the limit and turn this into an approximation, and multiply with delta xi, and reorder. Now we're going to evaluate the sum. Let us type out the 3 first terms in the sum. We can replace f of x0 delta x0 with the approximation. Do the same for the second term. Now, these two will cancel. Replace the third term with the approximation, and these two will cancel. I hope you see the pattern. For each extra term we add, the inner terms will cancel. And we only keep the first and the last term. If we do it for every single term, all that would be left is minus f of x0 plus f of xn. Note that x0 is xs. And xn is xe. Let them change place. What is important here is that this expression does not contain any information about the sequence of points. All it contains is a start and end point. Looking at our graph, at this particular case, the green rectangles are a relatively poor approximation of the area. But as the approximation is the same for any number of points, we can increase the number of points. Now it looks like the area of the rectangles are close to the area under the graph. Also note that our approximation for the derivative should be better when delta x becomes smaller. Hence, we can claim that when the number of points goes to infinity, both the error in the area and the error in the derivative goes to 0. Therefore, we claim that when the number of points goes to infinity, it is no longer an approximation, but an equality. This is what we call the integral from xs to xe of f of x dx. Similar to the derivative, we change from delta x to dx in the limit. If you are a true mathematician, you should also prove that the error actually goes to 0. But we'll skip that here. The sum we use to calculate the area is called the Riemann sum. We can replace the area with the integral, which gives us the classical formula for solving 1D integrals. The formula states that the integral simply is the value of the primitive function at the endpoint minus the value at the start point. It's also common to write f of xe minus f of xs with a square brackets with the xs as subscript and the xe as superscript. We can also write the integral of the derivative as f of xe minus f of xs. In the first example, we used uniform spacing between the points. But is this necessary? Let us try another point distribution. And increase the number of points. We can see that this one also converges to the area under the graph. The only condition we need is that all delta xi should go to 0 when n goes to infinity. If we continue and look at the expression for the integral, we can now let xs and xe swap places by taking the integral from xe to xs. From the expression for how to calculate the integral, we see that this changes the sign of the integral. How does this relate to our area under the graph and our Riemann sum? Since xe now is the starting point and xs is the end point, the sequence of points has to go in the other direction. This would give us negative values for delta xi. And the area would be the red negative area instead. This is an example of the limits of the area visualization, as it requires that the endpoint is larger than the start point, while the integral works in both directions. Next up, let us look at what happens if we split the interval and add the middle point, xm. The blue part is the integral from xs to xm of the function. The red part is the integral from xm to xe of the function. As we can write that the integral from xs to xe equals the integral from xs to xm plus the integral from xm to xe. The next question is, Why would we want to do that? Let's say that our function is not continuous at the point xm. Then the derivation we did would no longer be valid, as the cancellation in the Riemann sum only works if the function is continuous. If there is a discontinuity in the function, we have to divide the integral into parts where each part is continuous. The integral without the start and end point is sometimes called the antiderivative. This is because f of x can be written as the derivative of the integral of f of x. Or, if we integrate the function and then take the derivative, we get back the same function. But what happens if we reverse the order and first take the derivative and then the integral? Remember that the derivative of a constant is 0. Hence, d dx of f of x is the same as d dx of f of x plus a constant, c. As an example, assume that df dx is 2x. This gives that the primitive function is x squared plus an integration constant c. We would need additional information to determine the value of this integration constant. Next up, we are going to talk about some techniques for solving integrals. The first one is integration by parts. The derivation is quite straightforward. Start from the product rule for derivatives and integrate each term. This is the integral of a derivative, which is the function itself. We do not need an integration constant here, as each term will give a one integration constant. But the sum of three constants is just a constant. Hence, we only need to include the integration constant for one of the three integrals. Move this term to the other side. This is the formula for integration by parts. If you do it with limits, it looks like this. Let us show an example to demonstrate how it works. A classical case is the integral of log x dx. Start by multiplying the equation with 1, which does not change anything. Identify f of x as log x. If you know our derivatives, log x has the derivative 1 over x. Identify dg dx as 1. This means that g of x is the integral of 1, which is x. Integration constant is not needed here. F of x times g of x is log x times x. The integral is the integral of 1 over x times x dx. Cancel the x. The integral of dx is x. Now at the final stage, we add the integration constant. This is the primitive function of log x. Let us move on to substitutions, which is a very powerful tool for solving integrals. The idea here is similar to the chain rule we had for derivatives. Integrate both sides. The integral of a derivative is the function. I think it's easiest to illustrate substitutions with an example. Let's say we calculate the integral from a to b of f of x dx, where f of x is 4x squared. To illustrate the substitution, let's rewrite this as the integral of 2x squared. Now set u of x to 2x. This means that we can create a new function h of u of x, which is equal to f of x. And we can insert u of x instead of 2x. Let us call the start point f of a. This should also be h of u of a. And since u of a is 2a, we can write it as h of 2a. The endpoint is f of b, or h of u of b, which is h of 2b. We can now plot the function h of u. Its start point is 2a and the end point is 2b. This means that h of u is scaled with the factor 2 in the x-axis direction, while it has the same value on the y-axis. Hence, we can write the start point as u of a with value h of u of a, and the end point u of b with value h of u of b. If we check the area under the graph, we can however see that the green area for f of x is half the blue area for h of u. The issue is that we still have dx here, but want to integrate over the variable du. Let us multiply and divide by du, and change so we get dx du. This will be our scaling factor that will correct the size of the integral. We can calculate du dx to 2. However, we have dx du here. For 1D derivatives, this is 1 over du dx. Next, we should update the limits. We see from the graph that we are integrating from u of a to u of b. Now, when we have rewritten it as a function of u, we can drop that u is a function of x. Insert the derivative. And we see that we should divide by 2. Hence our actual integral is the purple line. Now the substitution is completed and the green area will be equal to the purple area. To solve it, insert expression for the limits. The primitive function will be u cubed over 6. And insert the limits. I'll leave it up to you to integrate the original function f of x and check that the answer is the same. Let's do another more useful example to demonstrate substitutions. Integrate x times e to the power of minus x squared dx from 0 to a. This function looks like this, and we want to know the green area. Our substitution will be u of x is x squared. This gives us the u dx is 2x. A trick one can use to simplify the substitution is to write dx as a function of du. Our start point is u of 0, which is 0. Our end point is u of a, which is a squared. Now we can start by replacing dx with our expression for it. And notice that the x will cancel. Next is to update the limits. And we replace x squared with u. This will give the following function in purple. We know the primitive function of e to the power of minus u. And the final answer is minus e to the power of minus a squared over 2 plus e to the power of minus 0 over 2. E to the power of 0 is 1. If we look in the graph, we have that the purple and green areas are equal for all the values of a. The next topic we're going to talk about is placing the derivative inside the integral. Assume that capital F of t is the integral from a to b of f of x and t dx. Now let's take the time derivative of both sides. My question is, would it be the same if we move the time derivative inside the integral? Since f is a function of two variables, we would write it as the partial derivative with respect to t. Let us draw an example integral given by the green area. Assume that f changes with time according to the animation. If we look at the Riemann sum, we know that the derivative of a sum is the derivative of each term. Hence it looks like this is true. But the condition is that delta xi stays constant, otherwise we need the product rule. Instead of trying to solve the Riemann sum with the varying delta x though, let us consider what would cause it to vary. That would be if the limits a and b changed with respect to time. The general case is therefore to add that the limits can be functions of time. To determine how much they change, start by looking at the start value a. Here the function value is f of a and t. The change in area should be the height f of a and t multiplied by how fast the start point moves, d dt. Note that we get a minus sign, as positive velocity of the start point will cause the area to decrease. We can do the same for the endpoint with height f of b and t. The change in area is the height times the velocity, db dt. This time with a plus sign, as positive velocity increases the area. Hence, we have three options for a time derivative. Change in function value f, change in the start point a, and change in the endpoint b. Finally, we are going to talk about the partial derivative. The first thing we're going to note is that the delta x we divide by is the same for the partial and total derivative. This is promising that we are going to integrate it. Let's take an example vector field v. Assume that the vector can be written as the gradient of phi. The condition for this to work is that v has to be irrotational, which it is here. Now we want to calculate the value of phi by integrating the vector field v. Start by setting up the equation for the x-coordinate and integrate all terms with respect to x. This works as delta x is similar in the partial and total derivative. This term has no x dependence and is the integral of a constant. This term is the integral of x times a constant. And this term just becomes phi. As it's a final integral, we need to add the integration constant though. However, this time it's not really a constant, as the partial derivative with respect to x considers both y and z as constants. Any function of y and z would be removed by the partial derivative. Hence, the integration constant is the function f of y and z. Let's repeat for the y-coordinate. Integrate as before. This is the integral of a constant times y. This is the integral of a constant. Finally, this becomes phi again. But now the integration constant is a function of x and z as we integrate with y. And last, the z-coordinate, which we integrate again. This is a constant times cos z, where cos z integrates to sine of z. This is just z. And finally we get phi, with an integration constant as a function of x and y. Now it's time to collect all terms. The first term, xy squared sine z, appears in all three expressions, and we can place it in the final expression. The x squared y term appears in the two first and could be a part of h of x and y. The z term only appears in the final expression, but could be a part of f of y and z and g of x and z. Finally, we could still have our classical integration constant, which really is a constant. This is an example of how we can reconstruct the scalar phi. As long as the vector field is irrotational, it should work. This is the final example in this video. Next up, we'll talk about line integrals in multivariable calculus. Thank you.